Alright, this will be the last video of the week. There won't be one tomorrow. But I'm going to give you kind of 2 assignments to work on, so you'll have stuff to do tomorrow. And although it's only 4 problems on each assignment, it'll probably take you the whole period to try to figure them out. And I'll expect you to, if you don't know stuff, maybe Google things or look up things and try to figure it out if you can't, and work together. Because this section, there's really no new math. This is the physicsy portion of it, so it's kind of cool. I like it. It's velocity. Velocity and other rates of change. I had to get my clipboard so my paper wouldn't slide around. Basically, this is all about, well, derivatives. Derivatives are rate of change. Rate of change is slope, right? So derivatives are all about slopes and rate of change. Velocity is the derivative of position. I kind of mentioned that before. If you've got a graph of position versus time. So like, here's time. And this is position, or so like if you start in Warden and you start driving towards Seattle, right? Well, it wouldn't be linear, it'd be something weird, I don't know. But anyway, if you take the derivative of that, derivative is slope. So if this is miles and this is hours, the derivative of that would be miles per hour, right? Slope, rise over run, miles per hour. So if this is position, this would be, your derivative of that would be velocity. So that's this, because this would be miles per hour now. Sorry, my wife is making a lot of noise. I hope you can still hear me talking.
What are the plants?
And this would still be time here. Alright, so if I do the derivative of position, like, so if I have a function, if I had like f of x equals, we'll just do the old x to the third. Makes it easy. So let's say this was something weird. Then your derivative of that, your velocity function, would be here. What we should call this. I don't know why, but in the book, that for the position function they always use s of t. And then for velocity function, makes sense, it's v of t. So that would be 3x squared. Then if we do the derivative of velocity, so the slope of that, so let's say we had something like that, the slope would be miles per hour, which is miles per hour squared. That's acceleration. And acceleration is the rate at which your speed is changing. So it's the rate at which your velocity is changing. Velocity is the rate at which your position is changing, right? These are all rates. If you do the derivative of velocity, so v of t, we'd have a of t. The acceleration function would be like 6x. So it'll be a line, whatever. Bring this up again because a lot of these problems, it's going to ask you things like find the acceleration whenever the velocity is 0. And so you're going to have to find, you're going to use your functions. So for example, if it said find the velocity, or find the, I said that backwards, find the acceleration at the times where the velocity is 0. Well, that wouldn't make sense. I don't know, stupid example. Let me just do some example problems that are trying to make up stupid ones, because then it won't work. So, you're going to have to know some words in this. Things like displacement. It has a few different meanings. In these problems, it's just the distance something has moved over a specified time interval. So how far you moved over a certain amount of time. So how far something moved over a specified interval. Does that make sense? And that's different than position, because if your position is 0 in Warden and then you drive to Seattle and now you're, I don't know, 200 miles away, we could ask for your displacement for the last hour of your drive. So that would just be how far did you move for the last hour or something like that. That it's just a shorter piece of the puzzle. I don't know. It'll make more sense when we do example problems. So you should already know average velocity, which some of you bombed that part on your quiz. That's just change in position divided by change in time, right? Drive to Seattle, average velocity is probably around 60 miles an hour. 200 miles, or 180 miles, let's say, divided by 60 miles an hour, that average velocity is 60 miles per hour. Versus instantaneous velocity, remember, it's the velocity at exact moment in time. We talked about that a lot. Speed is different than velocity. Speed is your absolute value of velocity. And the reason there's a difference, a lot of these problems will talk just about a particle moving along a line. It just simplifies motion. Instead of talking about a car or someone running or something, it's just here's a dot and it's going to slide back and forth along this line, and we're going to talk about the way it's moving. So if it moves this way at 10 meters per second, and then it stops right here and then decides to start moving this way at 15 meters per second. But when it starts moving to the right, the velocity is 10 meters per second. And then when it starts moving when it stops and turns around and starts moving to the left right here, the velocity would be negative 15 meters per second. So velocity has direction with it. It can be positive or negative. And like you could talk about a rocket flying up. When it's going up, the velocity is positive, and when it's falling down, the velocity is negative. Speed is just the absolute value of that. Speed is just how fast it's moving. So in this one, the speed is 10. When it shifts and turns the other way, speed is 15. That's the difference between velocity and speed. And let's get to the examples. I'm going to get on with this. I'm just going to do a couple right out of the book. Explain them. First one, example 4, page 130. Dynamite. I haven't done this yet, so this could be interesting. See how many times I mess up here. Dynamite propels a heavy rock straight up. I like to draw a picture on these. It's great to draw a picture. So you got a rock flying up in the air because there was an explosion. Now a rock shooting up in the air. So it says it shoots it up at the launch velocity of 160 feet per second. And it reaches a height of, so they give us the position function, S of t equals 160t minus 16t squared after t seconds. So that's our position function, right? If we plug in times, like if we plug in 0 for t, we get 0 because the rock would have been on the ground. After 1 second, if I plug in 1, I'd have like 160 minus 16, it's 100 and, what is that, 44? So after 1 second, the rock would be 144 feet in the air. And we can sit there and we can plug numbers in and we can figure out how high the rock went. That's our position function. That's what it's for. Want to know how high it is? Plug in the time for that and you'll know how high it is. Kind of like that whole concept of, want to know what y is? Plug in x. Alright? So, question A asks, how high did the rock go? Well, you could sit there and plug in numbers. Plug in 1 second, 2 seconds, 3 seconds, 4 seconds, and eventually it's going to start coming back down. It's a quadratic, so there will be a vertex. Finding that can kind of suck unless you have a method. This is position, so we could find the vertex of this. I mean, you could do like completing the square to find the vertex of the parabola. That would work, but let's use our calculus. When the rock reaches, you have to think on these. This is the hardest part about these. You have to think what's happening here. How do I find this moment in time? And that's why I'm only giving you 4 problems a day, because you might have to talk about these and figure out what do I actually need to do to find what it's asking me. That's the whole thing about these problems. So how high did the rock go? It's going to go up, and it's going to stop, and it's going to turn around and come back down. The key point is when it stops. If we know when it stops, the velocity is equal to 0. Right? Because it's going to go up, we're going to have a positive velocity, it's going to stop, and then it's going to come back down, and we're going to have a negative velocity. So if we could figure out the time at which the velocity is equal to 0, we can then take that time and plug it into our position function to get the maximum height. So we need a velocity function. So that's just the derivative of position. So v of t, taking the derivative of that, 160 minus 2 times 16 is 32t. There's my velocity function. Well, we want to know when the velocity is equal to 0, so 160 minus 32 t equals 0. Set it equal to 0, solve for t. So you subtract 160, divide by negative 32, and I think that's 5. So that tells us after 5 seconds the velocity will be equal to 0. So boom, blows up. 5 seconds later it's going to stop and start falling back down. Well, that doesn't tell us how high the rock went. It just tells us that the highest point it reached was after 5 seconds. So now we just plug that in to our position function. Do s of 5. 160 times 5 minus 16 times 5 squared. And what is that? 800. 25 times 16. I don't know what that is. 256, maybe? No, that's too small. I should get a calculator. 250 and it's 500? Is it 500? 400. It's 400. There it is. Don't need that. So we get 400. So S of 5 is 400. What are we in here? Feet. So that would be its highest point, 400 feet. B asks, what is the velocity and speed of the rock when it is 256 feet above the ground on the way up and on the way down?
Who cares?
Shut up. So we got when it's 256 feet off the ground, how fast is it moving, basically? Or what is the velocity and speed? So we're trying to find velocity and speed. Well, the speed is just absolute value of velocity, so this will be easy. So when it's 256 feet off the ground, the whole thing we got to work with here. These are our variable here is t, so we need to figure out how much time did it take for it to get to 256 feet off the ground. That'd be the way to go here. You're loud. So use the.
Think I'm not even talking.
Use the position function, right? That's 160t minus 16t squared. When that's equal to 256, we'll solve for t to figure out the time it took to get up to 256 feet. We should get 2 answers here because it's going to go up, it's going to pass, starts at the ground, goes up, it's going to pass 256 feet, it's going to reach a highest point and fall back down, it's going to hit 256 feet again. And we see we have a quadratic, t squared and t in the same equation, so the only way to solve this is, you might think you need to factor negative 16t squared plus 160t minus 256 equals 0. You could factor that, or or you can plug it into your calculator, graph it, find the zeros. Remember, here's a quick little review on that. Assuming this is a calculator problem. Negative 16t squared plus 160t minus 256. Graph it. Oh, there's my 2 zeros, right? We want to know when x is or t is equal to 0. So we get second calc 0. You got to do the whole left bound, right bound thing. I don't even see my cursor. 2. That looks like it's about 2. So if I go to the left of 2. There we go to the right of 2. There we go, guess, I don't know. Oh, 2, 0. So t equals 2. You could also factor out a 16 of this and then factor it. You could try that way if you're not feeling this. Get the other one, calc 0. That looks like about 1, 2, 3, 4, 5, 6, 7, 8. So I'll go to like 6. Go to the right of 8. There. Yep, it's 8, 0. So t equals 2 and 8. So those are the times the rock passed 256 feet. But we wanted the velocity at those times. So now that we have the times, we just use our velocity function. Do v of 2, 160 minus 32 times 2. So what's that, 64? So 96. So it's 96 feet per second when it was passing there. And then we also do v of 8. So 160 times 32 times 8, which is negative 96. That makes sense. On the way back down, the velocity is negative. Speed, 96 of both, right? Who cares? Who cares about that part? A lot of stuff here. C, what is the acceleration of the rocket anytime t? So we want acceleration. Well, acceleration is just the derivative of velocity. So we just take that function, v of t, do the derivative of it. Well, that's a constant, so that's 0. So a of t would just be negative 32. Right? Just a t, so just the derivative of that would just be negative 32. That'll be in feet per second squared. So that's the constant acceleration. At any time during the flight. That's because after the explosion, as soon as the rock starts moving upward, the only force acting on it is gravity. And gravity is about negative 32 feet per second squared, pushing down on it while it's flying.
Oh, it's a rocket?
It's a rock.
Oh.
It's just a dynamite went off and a rock is flying in the air. It could be a rocket, but a rocket has an engine, so the rocket's going to continue to accelerate upward while the engine's burning. This doesn't have an engine. D, when does the rock hit the ground? This is another one of those where you got to think, well, what is it asking me? How do I find this? Well, you can think when it hits the ground, not only is velocity 0, but is it position 0? So I would just use the position function, set it equal to 0. Didn't we already do that? I feel like we already did this. There it is, 16t squared equals 0. Maybe we didn't do this. Did we do this over here? Nope. We did the velocity equal to 0. So yeah, it's just position equal to 0. Again, you could plug it into your graphing calculator. You could factor it. We'll factor this one. So it'll be 16 times, what is 16 times 100? No, 10. 10t minus t squared. That's not factorable. Well, plug it into the calculator. Oh wait, yeah, that's factorable. Duh. Pull out 16t. So that'll give you 10 minus t equal to 0. Set each factor equal to 0, and you'll get t equals 0. Duh, it was on the ground when time was 0. And then that one at minus 10 divided by negative 1, so t equals 10 seconds. So we'll hit the ground after 10 seconds. Okay, doing one more example. That was a long problem. 18 minutes on one problem. One more, just because you've never seen anything like this before. Particle problem. It's right in there. Next one. Particle motion. Particle moves along a line. Told you there's a lot of those. It's just a dot moving back and forth along a line. Talk about the ultimate who cares. But they use this to represent a lot of different things. So it tells us it moves along a line. So the position at any time t greater than 0, so no negative times, let's see, is given by the function. Oh, so they give us the position function again. T squared minus 4t plus 3. S is meters and T is seconds. Okay, cool. Find the displacement of the particle during the first 2 seconds. So there's that word displacement. It's just asking how far did it move during the first 2 seconds. Well, we don't care about velocity here, we just want to know how far it moved. This gives us the position, so all we have to do then is find the position when it started, find the position when it ended, subtract them, and that'll give you the displacement, or how far it moved during that time. So during the first 2 seconds, we'll start at t equals 0, and if I plug in s of 0, 0 minus 0 plus 3, I get 3. So this thing's starting at 3 meters. So like if this is 0, here's 1, 2, 3, that's where it's going to start. And then after 2 seconds, so at 2 seconds, plug in 2 for t, so s of 2, 2 squared is 4, minus 8 plus 3, 4 minus 8 is negative 4, negative 4 plus 3 is negative 1. So after 2 seconds now it's at negative 1, so it's going to be over here. So here at negative 1. So the displacement then is just how far it moved. Well, it moved to the left 4. So that would be, the displacement would be negative 4. Or no, it wouldn't be negative 4. It would just be 4. Or wait, we should say negative. The displacement has direction, that's true. So it would be negative 4 meters. So it moved to the left 4 meters from when it started. B, average velocity during first 4 seconds. Again, it's average velocity, so that's just, change in velocity over change in time. So during the first 4 seconds, we need to find the velocity at 0 seconds. At t equals 0, what's the velocity? At t equals 4, what's the velocity? And then we'll do change in velocity over change in time. That gives us our average velocity. So v, guess what? We need the velocity function. Uh-oh. Scary bear? Yeah? So velocity is just derivative of position. So derivative of that's 2t minus 4. So there's our velocity function. Plug those in, so plug in 0, you get negative 4. And that makes sense, because right when it started, didn't we figure out it was moving to the left? Oh, we got a negative velocity. Here, plug in 4, so 4 times 8 minus 4 is 4. So now the velocity at 0 was negative 4, the velocity at 4 was 4. We should put units on these, I guess. So our average velocity is just our change in velocity over change in time. So 4 minus negative 4 over 4 minus 0, we get 8 over 4, which is 2 meters per second, would be our average velocity. What's next? Instantaneous velocity when t equals 4. So we just want to know, what is the velocity when at 4 seconds? Well, we just did that. We got our velocity function, we plugged in 4 for t, and we got 4 meters per second. That's the answer. At 4 seconds, it's going 4 meters per second. Oh, you alright? During that brief break, I just realized I did B wrong. I didn't do average velocity. I just did meters per second over seconds. That doesn't make sense. This is average acceleration, right? This is if you do the change in velocity over time, that's acceleration. We needed to do the change in position over time to give us velocity. I just screwed you all up, didn't I? So we didn't need this. I was going too fast. We needed to use this. So S of t equals t squared minus 4t plus 3.
Embedded value.
Our position at 0 seconds was 3. Our position at 4 seconds is 4 squared 16 minus is 3. So from 0, so it looks like we didn't go anywhere. So then our velocity change in position over time. So 3 minus 3 over 4 minus 0, it is 0. The average velocity would be 0. Because at 0 seconds you were at position 3. After 4 seconds you were back at 3. So your average velocity during that time is 0. Alright. I was wondering why they would ask this right after this. Because if you get this one right, you don't know the answer to that one. Anyway. What's D? Acceleration when t equals 4. Well, we got our position function, our velocity function, just get the acceleration function. Derivative of that, I think it's just 2. I don't think I'm going too fast here. Well, when t equals 4, there's no t to plug it in, so it's just the answer's 2. Looks like we have a constant acceleration. It's never going to change no matter what t is. If this was like 2t, then we'd have to plug in 4, but so it's constantly getting faster and faster to the right. So it started out moving to the left, but the acceleration to positive acceleration means it's going to go faster and faster to the right. So it's going to go slow down, and then it's going to get faster and faster and faster. Oh, hey, I just did part E. Describe the motion of the particle at what values of t does it change direction? This is a long answer. Let's see. Describe the motion. So we know it started off moving to the left because from 0 to 2 seconds we got it moving over here. So it starts off moving to the left, and it says at what values of t does the particle change directions? It's going to change directions when velocity equals 0, right? So it's going to start off moving to the left and have a negative velocity. It's going to stop for a second, not a second literally, but it's going to stop, and then it's going to start moving to the right, and that's going to be the only direction change. And I know that because acceleration is constant, so it's going to just start off moving to the left. It's going to get slower and slower and slower, stop, and then go faster and faster and faster to the right. So there's only one position or direction change, and that's just when velocity equals 0. So if I do v of t was 2t minus 4, if I just set that equal to 0, add 4 divided by 2 at 2 seconds is when it changes direction. So when it wants you to describe the motion, you would need to write out, and I'm not going to do this for the sake of time. Starts off moving to the left. You could be awesome and give the velocity at that time. Let's say v of 0 would be v of 0, negative. Starts off moving to the left at negative 4 meters per second. At 2 seconds is when it stops, and then it starts moving to the right. And the whole time it's constantly accelerating to the right at 2 meters per second squared. And we're going to skip F. That's crazy. That's it. So 2 examples where I was probably talking way too fast. So for the next 2 days, you just get to try some of these problems. And on Monday, when I'm actually able to talk to you, then we'll talk about your 3.3 quiz and these problems and everything else. There's today and tomorrow. Just try these.
Bless you.
You know, I should probably change that to give you some odds so that you can look up your answers. I'm just poor planning on my part. I don't know, but I know those problems are good. So never mind. Just do those ones. Okay, bye.